Hey everybody, welcome to this short video where we're going to practice writing difference equations for different scenarios and then practice finding terms as well and kind of thinking about what these are representing. So first off, in our first scenario we have one that's kind of similar to what we did in our introduction. Let's see, so we have a woman is taking a prescription medication. There's an additional dose of 75 milligrams, that's important. So that's the first dose of the medication. Then it says after that, the daily dosages is only 35 milligrams. The other important thing is that the kidneys remove 20% of the drug each day. Oops. All right, so if we are trying to write a difference equation, the first thing that we should actually do is define what the n and the x sub n are. So in this case, we're talking about this person taking a medication every day, and the drug is being removed by the kidneys each day. So we're going to let n be the number of days. All right, and then our x sub n is going to be the amount of the drug in the body. And of course that is measured in milligrams. All right, so the defining the variables is kind of the first most important thing. The next thing we need to do is to write the two things. So when we're writing a difference equation, we should always have an equation that has n plus x sub n plus 1 equals something. So let's do that part first. So if the kidneys are removing 20% of the drug each day, that's this right here, that means that 80% is left over. So just like we did when we did exponential functions, we're going to do 1 minus 0.2 and get 0.8. And that number goes into our difference equation as the coefficient of the x sub n. All right? And then since this person is taking a regular dose of 35 milligrams, we add that onto the end. And the other important part of the difference equation is the x sub 0, which in this case is, there we go, 75 milligrams. So our difference equation, we make sure that we define what the variables are. We have our actual equation part, but then we call this the initial condition, the x sub 0. So your difference equation really needs both of these things here and here. All right, so then let's move on to the next situation. Maybe I'll do this one in blue just for fun. All right, so this one says, suppose a population of 1,000 fish in a certain lake is growing at a rate of 50% annually. Each year the population is reduced by 40% through fishing, but the lake is restocked with 500 fish. Okay, so A says we need to write a difference equation. So just like we did above, we should define our n and our x sub n. Why is my pencil not working? There we go. So in this case, n is the time. It's being measured in years. And our x sub n is going to be the fish population in the lake. All right. Now, kind of the easiest place to start is right at the beginning when it says that there is a population of 1,000 fish. That tells us exactly what our x sub 0 is. So we can go ahead and write that x sub 0 is equal to 1,000. All right, and then for the kind of equation part of the difference equation, the x sub n plus 1, we need to think about a couple of different things. So first, the population has a growth rate of 50% annually. So just like we did when we did exponential growth functions, we're going to change that 50% to a decimal, which is of course 0.5. And then that's the growth rate, so we'll add 1 to it to get 1.5. So, whoops, let's erase that. All right, so just due to the growth rate, we have x sub n plus 1, or the population next year, right? This is representing the population that next year is going to be 1.5 times the population this year. All right, and that takes care of the growth. Oops. Let me just fix that. Can you tell this is my first video? Thanks for your patience. So the next thing we have to think about is the fishing So since it's reduced by 40% through fishing, the population is, we're actually going to subtract that from our difference equation. Again, it's a decimal, it's a given as a percentage, so we'll write it as a decimal. And that's 40% of this year's population, right, which is our XN, and we're taking that away because those fish are physically being removed from the population, all right, through the fishing. There we go. All right. And then the last thing that we see here is the lake being restocked with the 500 fish. That means it basically at the end of every year, they're just taking 500 fish and adding them to the population. So kind of like the repeated dose of the drug up here at 35, we're just going to stick a plus 500 at the end of our difference equation there. There we go. All right. So this now, my highlighter, is our difference equation. That's actually not the best way to write it. The best way to write it would be to combine these two terms that both have xn in them. So we see that we have 1.5 xn minus 0.4 xn. So if we add those together, or really subtract, we get x sub n plus 1 is equal to, so 1.5 minus 0.4 would be 1.1 x sub n plus 500. So this is what we're going to use as our difference equation, of course, together with that initial condition. Whew. All right, so once we have our difference equation, we can look at kind of parts B and C. So B says to find the first 6 terms of the solution sequence, which is really just the sequence that corresponds to this difference equation. So of course we can start with x sub 0 is 1000. That was given to us already. So now when we want to calculate x sub 1, remember that we're going to use this difference equation right here. So x sub n plus 1 says we do 1.1 times xn, which is really just the number that comes before it, and then plus 500. So what that means down here when we have x sub 1, we're going to do 1.1 times 1000, right, which is the number right above it, and then plus 500. All right, and you can grab your calculator. I did this right before the video, and I got 1600. All right, so that tells us year 1 at the end, right, because the 1 is our subscript, there are 1600 fish. All right, similarly, we would want to calculate x sub 2. How do we do that? Well, we do 1.1 times the kind of output that we got right here, the 1600, and then plus 500. All right, so again, that's saying 1.1 times the previous year's fish population plus 500. And again, grab your calculator. If you want to follow along, you should check my work on this. So x2 is 2,260. Likewise, I'll just go ahead and write down the calculations for x3. We have 1.1 times that 2260, and then plus 500. So our fish population at the end of year 3 is 2,986. Oh, cool. All right, x4. We would do 1.1 times the 2986, and then plus 500. So when you do this on your calculator, this is kind of the first time that we have to worry about decimals. It actually gives you 3,784.6. Since we're talking about a fish population, it really doesn't make sense to talk about a, decimal 0.6 of a fish. So we're going to round that up to the nearest whole number. And then our x sub 5, likewise, we have to round this one. But we get 4,664 fish. All right, so even though we just calculated x sub 5, since we started with 0, we actually have all 6 terms now, which is what the first 6 terms, which is what we were trying to find. All right, so then we can move on to the last part of the question, which says what is happening to the population. So if we look at these numbers kind of in our sequence right here, we can see that it's definitely increasing. So we would say the fish population is increasing. And then we can also kind of apply some of the ideas that we learned earlier in the semester. Is it increasing at a linear rate? Is it increasing at an increasing rate, or increasing at a decreasing rate? So the way that we would determine that is to look at the differences, basically how much is the population increasing by each year. So it goes from 1,000 to 1,600 from year 0 to year 1. So that's a jump of 600. And then going from 600 to 2260 is actually a jump of, 660. And then we can see that the gaps between the successive numbers in our sequence are actually increasing. So we would say it's increasing at an increasing rate. We could also tell that from the graph. And we know that increasing at an increasing rate is concave up. What does that mean long term for the fish population? Well, not good things. It's going to be increasing kind of without bound, unless, something would come in to kind of stop that. All right, so that's where we're going to stop right now. Thanks for listening. As always, let me know if you have any questions. Thanks.